Okay, hello everyone. This video I'm going to show you the angle twist calculation, and this is an example from a textbook, example for 10.5, and this is very fundamental example for the angle twist calculation for the torque loaded member. Okay, and it says there is a cylindrical bar and is subject to a multiple torque on. And he want to calculate the twist of angle for the A on here of end A. Okay, but I think he's trying to say the angle twist of A with respect to D. Okay, that's why I think what he want to trying to say. Okay, and also they wants to also calculate the angle of twist B and A with respect to C. Okay, so let's draw a free body diagram of this problem first. Okay, so and I think the problem will look like this. Okay, so here is to do, do, do. And this is A, this is D, and here's BC. Okay, there is a counterclockwise rotation. Okay, counterclockwise rotation, counterclockwise torque. Okay, and it's 80, and B here is clockwise. So it's 150, and C is counterclockwise in 60, I think. 60, I think. Okay, and D is counterclockwise as well, so it's 10. Okay, and don't forget unit is kilonewton times the meter. Okay, so don't forget the unit. Okay, and okay, so for what's the formula for the angle twist rule? Remember that the angular twist is torque times the L divided by GJ. Okay, so actually in this problem there is the torque between the AB section. Okay, a torque between the BC section and the torque between the CD section cause the angle of twist. Okay, so there will be have a torque AB and torque BC and torque CD here. Okay, these three torque will cause the deformation, angle of twist in AB section, angle of twist in BC section, angle of twist in CD section. Okay, because right now I don't know the direction of this torque, so I just assume everything is counterclockwise. Okay, counterclockwise, that means positive. Okay, so and for this rod, this is the same rod, so they have the same G. Okay, and what is the G? Okay, and this G, okay, this problem doesn't give you the value of G, but he give you the name of steel. And in previously we have a similar problem in axial loading. The problem didn't give you the elastic or modulus, but it give you the name of the bar, so you have to look up the chart to find the value of the elastic modulus. And in this problem you have to look up the chart to find the shear modulus. Okay, and so the G is the shear modulus. Okay, yeah, and there is a chart in your homework. So, okay, so if you look at the homework and look up the A36 steel, the A36 steel, its shear modulus is 75 gigapar. Oh, okay. Okay, so that's the shear modulus of this rod. And what's the polar? J is the polar moment of area. Okay, so what's the polar moment of area? So this it's about your geometry of your core section. Okay, it gives a diameter. Okay, and for the polar moment of area, okay, we have two kinds of formula. If we give you the radius, it's pi over 2. It's RO to the power 4 minus RI power 4. And if the problem give you a diameter, it's pi over 32, DO4 minus DI4. And this problem give us a diameter. And this rod is a solid, no hollow, not a hollow one, so it's solid, so the di is 0. So the j is pi over 32 and times the 200 times 10 to the power minus 3 to the power 4. Okay, let's see. Do we have to calculate the value first? Okay, let's calculate the value first. So it's 1.57 times 10 to the power 4 and the n to the power 4. Okay, that's the j. Okay, so and do we know? Okay, because finally we will have the angle of twist of the AB section, angle of twist for the BC section, and angle of twist for the CD section. Okay, and then we need to find the TAB, LAB plus TBC times LBC plus TCD times the LCD. Okay, and GJ is the same, so we have the same values. Okay, 75 times 10 to the power 9 and times the 1 point. Yeah, it's yeah, the number is so large. Okay, so maybe I calculate here first. Okay, so I calculate the denominator here first. Okay, so G times the J is 75 times 10 to the power 9 and times the 1.57 times the 10 to the power minus 4. So what's the value here? Let me see. So it's equal to 1175 or 1175 or 11775 11775 and 00000. Okay, so it's 11775 000 11775 000 11775 000. Okay. And also this problem gives us the information for LAB and LBC and LCD. LAB is 3. Okay, LBC is 2. LCD is 1.5. That's from the problem description. So only thing left, we need to calculate the TAB, TBC, and TCD. Okay, so how to calculate TAB, TBC, and TCD? Once again, I just tell you this cross-section method. I think you heard this a lot. So cross-section, we got cross-section here, cross-section here, and cross-section here. Okay, so we calculate from the left. Okay, so let's draw a graph for each section. Okay, yeah, it's going to take a little time. So it's 80. Here's and here is yeah, it's kind of take a little time, but the 80 150. Okay, final one. Okay, 80 150 and 60. And there's a torque at the cross section. TAB, if I don't know anything, I just assume everything is counterclockwise. If I don't know the direction, I assume everything is counterclockwise. TCD. Okay, so let's do it. Okay, do the rigid body equilibrium of each section. So here it's counterclockwise, so it's 80. Plus TAB is equal to 0. Okay, so like what this tell you? Let's tell you that TAB is actually minus 80. Okay, and here is 80 and minus 150 plus TBC. Okay, so what's the TBC? The TBC is 70, right? Okay. Sorry, that's write it too fast. Okay, equal to 0. Okay, and let's tell you. Okay, and the final one is 80 minus 150 and plus 60 and plus TCD is equal to 0. So what does tell you? TCD is equal to minus 10, right? TCD minus 10. Let me see. No, not minus 10. What's the bad? I did it wrong. Minus 10, 80, 110真实 yeah, plus 10. Okay, it's not minus 10, it's plus 10. Okay, so it's plus 10. Okay, so we have the torque AB, torque BC, and torque CD. So we have put a value in there. Okay, so we put everything there. Okay, so put everything in there. So we will have the I think I erased the J here. So finally we will have the first of all we will have the phi angle twist the A with respect to D. Okay, you just add these three together. So TAB is minus AT, but don't forget the unit is kilonewton times the meter. Okay, so I want everything in Newton times meter, so I have to put the 10 to the power minus 3 here. Okay, and LAB is 3 and 11775.000. So this is 11775.000, and this is 70 times K, and times here is 2, and the final one is 11775.000. Okay, so it's 10 times 10 to the power 3 and times 2 times the LCD is 1.5. Okay, so I think I can erase here, erase everything here. Okay, so I think if using your calculator, you can calculate the angle twist of AB, angle twist of BC, angle twist of CD. Okay, so what's the value? Okay, what's the value? Okay, what's the value? What's the value? Okay, if you use your calculator and push your calculator correctly, I think you will have the minus 0.020382 and plus 0.0119 and the plus 0.00127. So there's an angle twist for AB. This is angle twist for AB. This is an angle twist for BC. This is an angle twist for CD. Okay, so you add them together. What's our final value? Our final value add them together is minus 0.0072712. And the unit is I don't have the unit. I don't have unit. Actually, the unit is radian. Okay, I think I didn't put a radian here, but actually radian has no unit. Yeah, radian has no unit. You have to keep this in mind. Yes, a unit is radian, but radian has no unit. Yeah, yeah. Well, I think the sentence is very weird. The unit is radian, but radian has no unit. Okay, you know what I mean. Okay, so let's see. AC is so if you want to AC, so just add these two together. Okay, if you want to find AC, you just add these two together. You will have the phi AC. Okay, the phi AD is add these three together. Okay, I think that's correct. And for AC, you just add these two together. You will get the minus 0.00848.2. Okay, that's the. If you add these two, this give you 5 AC, this value. You add this in together, let's give you this value. Okay, here. Okay, so here's the example for the angle twist calculation. Yeah, once again, yeah, your cut section method is used a lot. Okay, you have to get used to this analysis. Okay, it's used a lot in mechanics of materials calculation. Okay, just start the video here and see you in another video. Bye bye.